Okay, yeah. Thank you everybody for coming to the ARC seminar. Today we have Elijah Kane to talk to us about kids for the infrared.
Thank you, Kyle. I'm talking about kids for the far infrared, and that doesn't mean I'm going to make children observe through a telescope. That just means we're going to use detectors called kinetic inductance detectors, which I will explain that acronym further in a bit. But first off, I just want to talk about like what we actually want to observe with the kinetic inductance detectors. So you might not have seen this plot. You might have seen the right side of this plot before, CMB, cosmic microwave background, which is, I guess, the most well-known part of this plot. If you just point a receiver, microwave receiver, anywhere in the sky and integrate for long enough, you'll see the black body spectrum. That's the right side of this plot. But I guess lesser known is the fact there's other cosmological backgrounds. So we have in blue the optical / near infrared background, and in red we have far infrared and submillimeter background. And I guess next let's talk about where these come from. So I guess the main idea is that the far infrared comes from dust emissions because any galaxy is going to have with young forming stars or outputting strongly in the optical and UV. But often they're surrounded by dust, right? Because that's the material they form out of is dust and molecular matter. And so what's going to happen is the dust grains near the stars will absorb the optical and UV over a pretty large range of wavelengths, and that will heat the dust and gas and re-emit it in the infrared. So in this plot here, this blue region represents kind of the energy that's taken a bite out of the star. The optical UV light from the forming stars gets re-emitted in this red region here just due to dust thermally heating. And on top of that, you can see that we have these spiky fine structure lines. So several elements, we got oxygen, ionized carbon, ionized nitrogen, so on and so forth. And these get collisionally excited due to the thermal excitation of the dust and gas from the star. And actually a full 50% of the optical energy from a galaxy ends up in the far infrared. So it's a great place to look to understand, forming stars, especially as they're obscured by dust in most cases. Okay, so specifically in the far infrared, I want to talk more about these fine structure lines. So the reason they're a useful tool for a useful observational tool is that as fine structure lines, they're splittings of an angular momentum level. So I've just attached a screenshot of the hydrogen atom here, n = 2 level. So due to spin orbit coupling, this level split into two, and they'll still have the same angular momentum number. So just by the rules of the selection rules, this was a forbidden transition, which means if you emit a photon with this energy, it's not going to readily be absorbed by other ionized atoms in the gas. It'll pass through because the likelihood of the one photon excitation event is technically prohibited for this transition. So it's collisionally excited, but then as the photon escapes the gas, it's not really going to interact much with the rest of the atoms. And so this allows you to study astrophysical processes for which dust is obscuring the optical and UV. And if you look at, for example, an example galaxy here, which is actively forming stars, you're going to see these lines indicated in blue. These all correspond to ionized atoms around, in the dust and gas around stars, which are readily being excited by this process, this collisional excitation. And in red, we also have higher ionization energy atoms. So these are ones that typically you'll find in a really high energy region, such as an active galactic nucleus or near a black hole. So these typically are associated more with accretion processes from an AGN. So the far infrared spectral lines give you kind of multiple things you could study, multiple energetic processes you could study in an active galaxy. And the final bonus is that since they have a well-defined rest frame wavelength, they unambiguously determine a galaxy's redshift. So if you see, say, this C2, this carbon-2 line at 150 microns, and you see it at 200, you know exactly what redshift it's at. You know how far away that galaxy was, kind of what epoch of the universe that radiation is being emitted at.
Maybe naive question, but what if something got redshifted enough that is there any chance that you would confuse it with one of the other lines?
Yeah, I think typically you need like more than one line. You kind of need like another good example is like the or carbon monoxide like rotational spectrum. Like it has a whole spectrum of lines with well-defined spacings. If you see like 2 or 3 of those, you know kind of what redshift it's at.
Sure, makes sense.
Okay, so just an example. This is from James Webb. So this is more in the shorter infrared wavelengths here, but it's a kind of close-up picture of star forming region, or what we sometimes call a photo dissociation region. And the reason we call it that is because this optical UV light from the massive star cluster here is fully ionizing like most of the atomic gas. Well, first of all, the gas really far away is molecular. We have like H2, carbon monoxide, the cool gas that stars form out of. As you get closer to the star, it dissociates these molecules, so we get neutral hydrogen, get neutral carbon, neutral oxygen. And as you get really close to the star, it's going to ionize these neutral atoms and knock off an electron or two. So basically, if you have just the eyes here represent the number of electrons that have been knocked off. So 1 means neutral, 2 means singly ionized, 3 means doubly ionized, and you're just going to get higher and higher ionization energies available the closer you get to the star. And as we said before, these ionized atoms have these fine structure transitions, which lie nicely in the far infrared. So, 10 to a couple hundred microns or so. And I guess the final bonus is we can combine observations of active galactic nuclei and star formation, because lines corresponding to AGN and to star formation both fall within this far infrared range. And so this will help answer sort of a question that's ongoing in astrophysics, is what's the relationship between AGN activity and star formation? Because the role of feedback, basically AGN is a highly energetic region at the center of a galaxy where there's inflows and outflows of gas, a lot of energetic processes happening. And it's not entirely clear why like things like the AGN mass and possibly the star formation rate correlate so well in the presence of this feedback. So I guess more observations would be useful. Okay, and to touch more on the point about measuring redshift, this is kind of the state of the art of far infrared measurements. Is the Herschel probe. So this was a space probe in the 2010s that was in this image observing kind of in the longer submillimeter range, so 250 microns and above. But the point here is that there's so many galaxies, and there's like an uncountable almost amount of galaxies in this image, because every pixel has emission, and it's so much so that the galaxies are kind of blurring together at this resolution, and you're what's called confusion limited, so you can't really resolve all the point sources. And this is kind of I guess to touch on the star formation point more, this wavelength range corresponds to redshifts of Z1 to Z equals 3, which, if we're talking about the history of like the star formation rate over cosmic history, this is roughly corresponding to like the time of the universe when star formation was most active. This is about 10 billion years ago, Z equals 2. And since then, it's slowly been declining. So this would be, a good redshift to measure to understand the star formation rates. But kind of resolving the redshift of each source, or like each pixel, will help us with this, because basically you take a data cube, each pixel in the data cube has a spectrum, and you'll see these lines relative to each other from the spacing between the lines and their like absolute wavelength. You can figure out the redshift and help resolve some of these sources, so that the source confusion is no longer an issue with this technique. Okay, so just to talk about current efforts in the far infrared or around this wavelength range, we got James Webb. That's the mid infrared, near infrared. So like I said, it's a bit shorter, 29 microns and below. On the upper end, we have ALMA, 320 microns and above, in what we call more of the submillimeter range. And in the middle of this leaves this kind of sensitivity gap between 29 and 320, where we are proposing to, kind of fill this in with a highly sensitive observations. The reason the measurements have to be so highly sensitive is because we have to go to space, essentially. The backgrounds on Earth are basically the atmospheric absorption is just way too high to do any meaningful far infrared observations. That's kind of this region right here is exactly where we are, at pretty much like 100% opacity. So that precludes any nice telescopes like you got on the radio.
Wasn't ALMA operating for a sub-meter?
Yeah, so the thing is that this figure doesn't really show very well, is that there are some, I probably should have chosen better ones. Yeah, there's some narrow yeah, like windows within the sub-millimeter, which do have pretty good transmission if you go to like a very high and dry place like Atacama or
There's no other place that could do all.
yeah, it just has to be like at the end of the earth basically, where there's no water and you get nosebleeds. But yeah, or bacteria.
There's like really limited bacterial secretion.
Oh, that's awesome. Yeah, it's basically you have to go to crazy places, or if you want to look even shorter wavelengths, you have to go to space. So just the way of the world. But once you're in space, you know, your noise backgrounds are obviously extremely low. The main thing we have to consider is that your limiting background is actually photon shot noise. This is just like random arrival times of photons, and it's coming primarily from zodiacal dust, which just means like dust in the solar system at about like an AU from the suns. That's like the asteroid belt, Jupiter, that sort of region. And we can predict how much noise we're going to see due to this. First thing we need to know is like how much power we're actually getting. That's pretty well modeled and projected here. So for like kind of standard spectrometer channel parameters, and at 1 to 10 terahertz, we get like an attawatt that's 10 to the minus 18 watts of power, which is tiny. And then the shot noise, which I'll explain this formula a bit later. You plug in the power, you plug in the photon frequency, and you get an NEP of 0.1 attawatts per hertz. So that is really hard to design a detector that is that sensitive, but we're going to try. Yeah, and the reason we're going to try is because compared to the most recent generation of far infrared observatories, so I'm talking like Sophia, that was a high atmosphere plane, and Herschel, that was a space probe. A 2 orders of magnitude sensitivity improvement is actually feasible, given like the last decade's worth of improvement in detector technology. And this is interesting astrophysically because it'll enable measurement of Milky Way type galaxies at Z like, you know, around the cosmic noon, around the peak of star formation in cosmic history. Which is, you know, it's going to help solve this problem, I guess, we currently have, where we're looking at more, I guess our samples are a bit biased because we're biased towards more bright point sources, and this will help us push that bound down. Help us also answer the questions I talked about a bit earlier, you know, about connecting star formation rate, AGN accretion rate, and also answering some questions about metallicity around cosmic noon, just because your lines trace also these like heavier elements like oxygen, nitrogen, silicon, etc. Okay, now I'm going to get into the meat and potatoes of what I know, I guess, the most about from spending ungodly hours in the lab, which is kinetic inductance detectors. So why do we call it a kinetic inductance detector? Well, the inductance part, I guess, is explained because it's a superconducting RLC resonator, or it's actually many of them coupled to a single feed line. So, you know, 1, 2, ... N detectors, one feed line, each coupled through this capacitor, which allows some energy to leak back and forth between your readout and the detector. So what you do is you put a sine wave in, or a series of sine waves, one corresponding to each detector. Or actually, I guess the first thing what we're doing here is we're just sweeping a sine wave across a range of frequencies and measuring how strongly each resonator absorbs the power at a given frequency. And I mean, kind of just the definition of a resonance is that it's, absorbing power. It's resonating with the feed line when you're putting in power at its resonant frequency, hence these dips in transmitted power. And so the way we actually see photons, the way we see optical power, is that it gets encoded in the fractional frequency shift, because what happens is you focus light onto this inductor. It through some processes in the superconductor, it changes the inductance and shifts its frequency through like 1 over root LC. And since separated in frequency space naturally. It's also just amenable to frequency multiplexing. Basically, what you do is just design each of these capacitors with a slightly different capacitance and hence shift its like resonant frequency. And the reason, I mean, it's not easy to make a superconducting system and keep it stable. And, I guess the question is begged, like, why cool something down that cold if you don't have to? The main reason, at least to my knowledge, is that the elementary excitations in a superconductor are many, many times lower than a semiconductor. And we'll see this is important for achieving a really good energy resolution, is having your kind of lowest level excitation be low energy, at least compared to the photon. Yeah.
How much does the quality factor of the resonators like matter to the Real system?
It matters a lot, actually. Yeah. Here I've drawn a very idealized system, but I guess you're always trying to design resonators with the best quality factor, just so you can cram more of them into like a given bandwidth. And the problem we actually have a lot of the time is that we don't quite get these capacitors correct, and so the resonant frequencies are off. And it's a very simple sounding problem, but it's really hard to correct because you then don't know which resonator is which if they like get close together. So yeah, Q is pretty important.
Is the Q of your resonator just that R term, or there's like
it's
this R, that cap, and like
it's some combination of like R and C, because it's basically like you add, like he represents a loss, so you add the different losses, like the rate at which a resonator loses energy through different channels. So one of those would be this like coupling capacitor, one would be the resistance, and so they kind of just like add in parallel. Yeah. So like they both kind of determine it.
Do you know like the order of magnitude of what that R is?
It would be calculable. I don't know off the top of my head, but you can calculate it from like superconducting theory.
Or like what the Q is.
Oh yeah, Q I guess typically is like around tens of thousands or 100,000 for. Cool. 100,000 is like pretty ideal, I guess, for what we do. Yeah, a lot of work goes into that.
I guess last question. What is the real frequency?
Yeah, around a gigahertz, straddling a gigahertz roughly. Yeah.
Oh my God.
Yeah, these are pretty cool little resonators. They work well. But yeah, here we just have, an actual device. So port 1, port 2, that's the in-out ports. And then, you have to zoom in to see these things. So close up, that's just on the bottom, coupling capacitor. And then this is the resonant circuit itself. That's C, that's L. This is like an interdigitated capacitor. So it's basically like this, two like sets of fingers essentially. And then there's some R in there just distributed, yeah, optical power goes here. Okay, so the way we actually, tell what's happening in these things is, like I said, we put a sine wave in corresponding to the roughly the resonant frequency of one kid. It interacts with the kid, some energy like sloshes back and forth, and it comes out the other side with a different amplitude and a different phase. And so the full schematic of our measurement setup looks a bit more complicated, but the basic idea is just this. You just put a V1 in one side, you put enough attenuation to not like, overload the detectors. You put enough amplification on the other side to like do what your mixer, or put the amount of power in your mixer that it wants, and then you just mix the two signals, and that'll tell you what's the transmitted amplitude, what's the transmitted phase. Here's just a picture of our actual cryostat setup so you can understand these different stages. So we start at the top 50K, and then each stage progressively cools down more and more until the detector stage at 100 millikelvin. So basically what you're doing is you're coming in the top here, going down the stages, it goes to the chip, which is mounted somewhere down here, and then comes back up with, some amplification and attenuation in between. And then all readout happens out here.
How big is that?
Is that like
4
feet, 4.5 feet?
Okay. So small.
5 feet? I'm taller than it by a bit, by like a foot maybe.
Okay. That's still a big device.
Yeah, it's hefty. There's a lot of layers that go. You have to take on and off a lot of layers every time you take a picture like this.
Oh,
but you get fast.
shields.
Yeah. Okay, so I guess this slide I just want to talk about what we actually see when we, or what, like kind of what aspect of the transmitted signal we actually look at, which happens to be well, I guess maybe I should just say this is the formula describing basically the complex transmission of a resonator. So this is just, you take the voltage at the other side of the kid divided by the input voltage, and you get this kind of, I guess, slightly gross looking formula that has an amplitude and a phase.
Under the assumption that both sides are.
Yeah, and you can account for that, but it gets grosser, so I didn't put it.
Yeah.
Yeah. So like it kind of ends up having this. So if you take the magnitude of this, and we usually plot it in decibels, which is just like logarithmic scaling, you get this nice dip here, which shows that the power is being absorbed at the resonant frequency. But then it's actually more practical really to look at it in terms of phase. So this is the real and imaginary parts of this transmission, because you see that so each of these blue dots is like an equal frequency spacing, and right here at this X is the resonance, and at the resonance you see that your change, like your absolute difference between these points, is a lot larger close to resonance. And the result of that is when you put in optical power, most of what's going to happen is that this frequency is going to shift. Like the quality factor is going to change a little bit. That's like a smaller effect, but mostly the frequency shift. And so if you're at a point where these frequency spacings are really large, you're going to get a pretty large change in phase, which allows you to sensitively measure the input power. Okay, so now I guess the reason we want to be tuned at such a sensitive point is because we do have noise like any system, and this comes in several sources. So the white noise, this just means it's equal at every frequency. Basically the spectral density is flat, and this comes in two forms, one of which is shot noise, which also has two sources. One is just from random arrival times of photons in your signal that you're actually trying to look at. The other is thermal noise in the inductor. And we'll get into why this is shot noise and not Johnson noise in a bit, but basically it's because the superconducting system itself is made of like discrete electrons that are combining and recombining. And then Johnson noise also present, that just comes from like, your amplifiers, your electronics, mostly from your first stage amplifier right after the kids. And then we also, in addition to that, have 1/f noise, which primarily comes from something called two-level systems, which are present in the capacitor. They're present in the substrate of the detector due to kind of non-idealities in fabrication. Okay, so just a quick review of what shot noise is. Essentially, you could envision it as a current that's made up of delta functions. So you have like charges going through a wire with some fixed kind of mean current, but at random times tj, they arrive with like a delta function spike in the current. And if we want to understand like the noise spectral density of this, the first step is to understand the autocorrelation function, which just means you're taking the signal, you're shifting it by a time tau, and then multiplying by itself and integrating. So if the signal is kind of correlated at time scales tau, you're going to get a large autocorrelation because it's going to match itself. If it's not correlated, it's just going to kind of integrate to zero. Okay, so I guess assume we integrate for some time t, and we get n pulses. If you evaluate this integral kind of hand wavily, you're going to get n, because n pulses multiplying by each other. You're going to get q squared because each pulse has an amplitude of q, and a delta function because if you don't line this up, the pulses are kind of infinitely thin. They're not going to overlap. And like I said, we assume a constant mean current, which just means this you can define like this I bar term, which is your number of charges per time. And the autocorrelation function is just that times the charge times a delta function. And that makes it really easy to calculate the spectral density through the, how do you say, Wiener-Khinchin theorem? I think that's probably how you say it. Basically, yeah, just the spectral density or the noise power at like each frequency is the Fourier transform of the autocorrelation. I think that's the proper statement of that. So plugging in, all it does is just add a 2, get rid of the delta function. And just I guess to explain what the spectral density is, if you're reading out with some bandwidth between frequencies f1 and f2, you just integrate the spectral density over that and you get the variance within that bandwidth. So this is kind of like the noise on your signal if you have a bandwidth of f2 minus f1. Yeah, and this is white noise because, you know, I wrote S of f here, but there's no f on the right side, so it's just spectrally flat. It's specialized to the case of photons. It's really easy. You just replace the charges with energy h nu, replace the current with the power, and yeah, you have the formula from earlier with units of watts squared per root hertz, because if you integrate this up over a bandwidth, you're going to get your variance in the power that's entering your detector. Okay, the next source of shot noise, I guess now we're going to delve a bit more into some superconductor stuff. So the first thing you need to understand is that the electrons in a superconductor, they, I guess below a certain temperature in a superconductor, it becomes actually energetically favorable for electrons to pair up and to become like kind of bosonic particles, which we call Cooper pairs. But it's not fully condensed because any finite temperature, we have thermal fluctuations cause them to break into quasiparticles. And I guess quasiparticles is kind of a confusing word because why not just call them electrons? But they're not quite electrons, but basically they're electrons. They're fermions. That's what they are. But they do that at some constant mean rate. So that's kind of these, I guess, Feynman diagram type processes here. Just a phonon, some bit of thermal energy hitting a Cooper pair, it breaks up, or they can recombine and emit some energy through a phonon. That's all happening in the inductor because this is the responsive area of the detector, which kind of basically if anything happens to the superconducting system in here, that's going to produce a shift in the resonant frequency, which is proportional to the number of quasiparticles. So that's the reason why we care about this process, is because this quasiparticle number is kind of the driver of the response of the kid. So it's easy to calculate the spectral density of this because we already have the formula for shot noise, and we just need to plug in the rate and the number. So per event, we get Q equals 2 quasiparticles, that goes to 4. And then there's some rate, which I'm just going to call gamma th, which you can, theoretically predict. I guess no reason to write it out here. Just there's some rate at which this is happening. And this isn't quite in the units we want if we want to compare it to our photon noise, because it's in units of like a rate of quasiparticles per time per hertz. But we want it in units of power. So to convert that, basically I mentioned that Cooper pairs are energetically favorable state. That just means that to break that pair, you need to put in an energy of delta per particle. So that's this kind of gap here. So that means the relationship between the power and the rate of quasiparticle production is just delta. So that's the energy per quasiparticle divided by some efficiency factor eta. So if your energy is going in to the inductor, it might leak out through some phonons escaping or something. So that's why that factor is there. And at the end of the day, our shot noise just gets multiplied by delta squared over eta squared. But basically, just this is kind of just proportional to the rate of thermal production. And yeah, there's one more final source of shot noise, just because these quasiparticles, they don't live forever. It's not an energetically favorable state. Eventually they're going to find another quasiparticle, recombine. But this happens independently of the generations. So it adds an additional term, but you can calculate it by just knowing that the rates of production and the rates of recombination have to balance. And all you do is just plug in, instead of gamma th here, you plug in gamma for your recombination, which will be, higher than your thermal rate if you are also breaking these, if you have some optical power incident and you're breaking pairs optically. Yeah, and that's just the expression for the total shot noise. And I guess now we're in a position to understand why we couldn't have used a semiconductor detector to detect this to reach this really low sensitivity level. So the first thing we're going to do is just work in some limits to simplify the expression we just came up with. So work in the low temperature limit. You can always, in theory, make your detector colder. In practice, you actually can too, to a point where the thermal noise is like subdominant. So we can just assume that gamma th is 0. and also assume perfect efficiency, which is probably never going to happen, but just simplifies the math a bit. So yeah, your thermal term drops out, and then if your eta is 1, then the NEP, the total shot noise NEP is just 2p. That's the power coming in. That's your optical power, and then it's the sum of your kind of elementary excitation or your photon. So that's like the particle coming in, and then your single excitation energy in the detector, which since the mechanism for depositing energy in a superconductor is to break a Cooper pair, that is just the energy taken to break that pair. So it's 2 delta. Some numbers for TC equals 1 Kelvin superconductor, which is kind of the ballpark we design these things around. The gap energy is just like milli-electron volt scale, which is well below the like tens of MeV scale for a terahertz photon. Whereas for a semiconductor, band gaps are EV scale. I didn't look this up, but I'm pretty sure it's true if I remember correctly, which is well greater than the photon energy, meaning you just kind of mathematically can't reach this shot noise sensitivity limit. Okay, and so if you were to just look at only shot noise, I mentioned that it changes mostly the resonant frequency, and it changes the quality factor a bit, which means the track that it's going to go back and forth on is going to be like slightly not parallel to the circle, but it's like approximately parallel. Just because Q it's like a real number in the numerator, so it roughly corresponds to like the amplitude, the radius of the circle. And then F is kind of the complex part, which is like rotating around. There's one more correction I actually have to mention, just due to the fact that quasiparticles don't live forever. And so if you calculate the autocorrelation function between these things, basically what that's going to do is you're going to broaden the delta function we derived earlier from like assuming the shot noise process is just made up of delta functions into something that's more like a two-sided exponential. And what that's going to do is just remove high frequency information above like the quasi-particle recombination rate. So at about 1/tau QP, you start rolling off, just because you need like every infinitely high frequency sine wave to make a delta function, but to make this more smooth looking thing, you only need some of the lower frequency ones. And I think when I learned this is when I realized that noise can be interesting, because all you do is just put your detector in a fridge, like run a signal through it, like it's dark, nothing's happening. But from that, and then you just take a Fourier transform and you learn like what's microscopically happening in the superconductor, which I think is pretty cool. Next up, amplifier noise, which at this point I'm going to kind of talk about things in terms of voltage, just because it happens at the very end stage of this readout chain where, to refer this back to what's happening like in the optical system would be a bit difficult. It's easier to just talk about the noise it adds on top of like your voltage that you're reading out. So there's two components, right? Because it's complex. It's a complex transmission. It's complex. It has like amplitude phase or real and imaginary parts. Either way you talk about it, both of these components are uncorrelated, and they're both Johnson noise, just because this is essentially due to like temperature fluctuation, or it's the like resistances in the amplifier having a finite temperature. And I guess I just put this formula up here to understand that you can make this noise source subdominant to other noises by just increasing PG. So, just putting more power in, you're going to get a better signal to noise by the time it hits this amplifier. And finally, the kind of 1/f region of the noise, the lower frequency noise, and this is usually the component that we worry about the most when designing these things, is a two-level system noise. And it's called that because at least the leading theory for what these things are is that they're atoms which can tunnel between two sites. So it's kind of just, you fabricate any material, like even if it's crystalline, I guess, like if it's very well ordered, even on the surface, there'll be some kind of like oxide layer, which is more amorphous, like more disordered. And you're going to have kind of randomly existing like randomly spaced out energy barriers where atoms can tunnel. So yeah, it's mostly present in the capacitor where we put down a bunch of dielectric to, get the large enough capacitance we want. And when you put down a lot of dielectric, you're going to have probably some surface oxide layer. Try as you might to not have that. And essentially when the atoms move between these two sites, they have, a dipole moment, which is just the charge times the displacement of this atom, which is changing. And so that changes the dipole of each two-level system. And then as the dipole moment changes, it couples differently to an electric field, which causes basically a shift in the dielectric constant, which means your resonance frequency is changing because your actual capacitance of this part here is changing. And I guess the interesting thing is, unlike the shot noise, which was happening in the quasi-particle system, we could tell this is definitely not something happening with like the superconducting, system in the inductor, because it's perfectly parallel to this IQ loop. It's like entirely phase noise, which means that the quality factor is not changing. If you had like Cooper pairs breaking, you had that process happening in the inductor. That means Q and F are both going to change. But for TLS, we just see like a low frequency spectral kind of 1/F shape that's only in the phase direction. Okay. Yeah.
If it's 1/F, why not increase that?
That is actually something people do. Yeah.
Because normally for our stuff, we're at a gigahertz-ish too, right? And we didn't think about 1/F. It's because we're not cryogenic, but it's so small compared to the Johnson phase.
Yeah.
It's just because you're so close, you beat down everything else, and now this 1/F mode is still.
Yeah.
It'd be like out of the size of that inductor, right?
Yeah, that would help. Like you push up. So I think what you're saying is you change the resonance frequency of the kid, because I think that people do that. Yeah.
What if you did it at millimeter wave?
Yeah. Well, I mean, actually, I think we're talking about maybe two different things. Like the F here is the frequency of like it's like the spectral PSD frequency. So this is like, there's a lot of frequencies here.
But I thought the PSD of 1/F noise was 1/F.
Yeah, but the kid's resonant frequency is different though. Like, I guess this is more of like the rate at which the resonant frequency is fluctuating. So it's like a frequency on top of frequency. But I think that actually what you said is true for like a different reason, that tuning, I think if you get like a larger capacitance,
it's a phase noise problem, right?
Yeah.
But if you're that make it worse.
Yeah, I get this like different frequencies mixed up in my head all the time too. There's just like too many of them in this problem.
This picture, and now your next slide.
This one? Yeah. So this is just like a comparison of the noise, the types of noise I talked about. So at low frequencies like 1 to 10 hertz, this TLS noise is dominant, and then if you're at some like relatively high temperature for this kid, then you can have like a shot noise comparable to that as well. And then down kind of the lowest limiting noise at high frequencies is just your amplifier. But actually we don't see all of this when we like take data in real life, because we only read out at 488 hertz, just because you can't take like an infinite amount of data per time with like 1,000 pixels. So you have to sample at some finite rate, which means you're going to see essentially noise contributions from up to the Nyquist frequency, which is just half that. And then on top of that, another strat for avoiding this low frequency noise is you do what's called chopping, where you basically just take like a black piece of paper or something equivalent, and then move it back and forth in front of the detector at a rate of like 10 hertz and difference it. So you just average on off, and that'll get rid of like fluctuations below the chop frequency. So anything below 10 hertz you're essentially not seeing the noise from that. You're removing it through this process. Yeah,
What's limiting your readout frequency?
just like the rate of data acquisition. Like there's
It's not, you can hear that.
There's a FFT you have to take somewhere, right?
I mean, we're doing an FFT, and you can buy an FPGA, $5,000 that can do a 4 gigahertz.
I can't say this is my strong suit.
Okay,
So I just know I know of like two.
games.
Yeah, because I know we've talked about like Casper or whatever like the FPGA system is. Like that's one system that's used, and that reads out at 48 hertz for this thing. Yeah, and
I'll
then
talk to you next week.
yeah, I'd like to know this too. Actually, there's like two systems I know of, which is the Casper one and like RF system on chip, which both sample at this rate. So I kind of just assumed it was like a fundamental constant, which I guess it's not, but
Yeah, I just want to get that because the ADCs in those things are the gigahertz ADC. They're cheap now. And that's really what I was saying. Like you're one over F noise, you sample at a gigahertz.
yeah,
Right?
but then it's limited by this chopping frequency too. Like it's how fast can you move like a blocker in front of your detectors. Typically like 10 hertz is kind of seems like the practical limit. Yeah.
Right, right, because you're integrating all the way down to
Yeah. Then I guess at some point you have to care about drift too, and you have to like calibrate your detectors once in a while. It's kind of a different problem. Yeah, so there's a few things you could do to kind of bring this noise down. I mean, number one, easiest one is just lower the temperature, which is going to bring the red curve down. Just because okay, this is math, but it's proportional to this rate of thermal generation, and the rate is like roughly proportional to the number of quasiparticles in the system times some factor here, which causes it to like the lifetime doesn't go up forever, the rate doesn't go down forever, it saturates some value, but essentially it's pretty much proportional to the number of quasiparticles, which if you have less thermal energy in the system, you're going to be making less of these things, so your rate is also going to go down, and your thermal noise will go down too. So kind of in practical like kid design, the NEP limit is actually set by this 2-level systems at the frequencies we're looking at. So there's kind of 2 ways to bring this down. Like first of which is just to understand that the 2-level systems live in like a surface layer. Like you put down this dielectric, which is mostly like a crystalline like silicon thing or whatever, and it's not really disordered, but you have a small disordered layer which hosts these things. And so one strategy is just decrease the volume of that layer. And also, since I'm not going to derive this, but the noise spectral density does end up scaling as 1 over the electric field strength, you just increase the field strength, and kind of the TLSs, the 2-level systems saturate out into a more stable state, and they're not going to fluctuate as much. And a lot of work's gone into this that I don't really understand. That's kind of yielded benefits over the years. Okay, so once we have a detector that we have designed, we've done all this TLS mitigation, we've kind of done what we can to bring down this noise. We want to actually figure out if we succeeded. So the first thing you do, you have to measure some sort of power spectral density, which just means you turn your detector on, it's in like a dark configuration, there's no light hitting it, and you're basically just measuring what are the dark, like the fluctuations of its resonance frequency when there's no power. And that's kind of the intrinsic, noise that's happening in the detector. But to map it to an actual power, you have to know like what sort of optical like energy corresponds to a fluctuation in resonance frequency. And that's sort of the calibration step, which you basically use to convert like an amount of, you convert this dF over F to watts essentially. And the nice thing about doing far infrared detectors is that you can use a black body because the peak at like 10 to 100 Kelvin is lying in this range. It's like between 10 microns and 100 microns. And so what we do is we just stick a chunk of metal in the fridge, put some filters between it and the detector, Make sure you epoxy the thing, so like, you know, it's actually a black body, not a copper colored body. And then, yeah, you just heat it up. So you just slap like a coil of wire on it. There's more calculation that goes into it than this. You have to like make sure you get the conductivities and heat capacities right. But the basic idea is you just heat a chunk of metal up that has like good absorption, and it'll have the spectrum roughly. Yeah, and you use that, you change the temperature of the detector, or sorry, of the black body, measure the frequency shift, and then once you've measured that, it's as simple as just dividing the this S dF over F, the spectral density of frequency fluctuations, by the responsivity, and you end up with the noise equivalent power. And to end with, I've just attached some of like our latest results for kind of a large array of kinetic inductance detectors where we're trying to reach down to this 0.1 attawatts limit. So this step is just measuring the responsivity. I guess plotted this way, you can't really see much of a change, but if you fit each of these using the formula I described earlier, you know, with the dF over F and the Q, you can back out like what's the resonant frequency of this, and plot it versus power. And there's some theoretically motivated model for how it should respond to power, which is just a simple like 2-parameter fit. That tells you, you know, how responsive is your detector to power. And then this is just the spectral density divided by that responsivity. So actually as a function of a sweep across powers. So at very low powers, sorry, this is essentially black body off. This is like a dark detector. And you can see it's flat. As you slowly ramp up the power, it gets in the photon shot noise regime where this is proportional to P. It's proportional to the, you know, it's like a Y equals X thing. And yeah, I guess also you could see that the shapes of these spectral distributions kind of follow what I showed earlier, where at really low temperatures, really low powers, you see just like a 1 over F type slope. And then as you increase the photon shot noise, it becomes flatter and flatter. You're seeing like white noise dominating above the TLS.
Is there a reason why? I presume the colors are the same as before, so the yellow is like higher temperature and the blue is low temperature. So it looks like towards lower frequencies, the power like goes down with temperature, but then kind of goes back up a little bit. It's very small, so it could just be fluctuations. I don't know.
Yeah, are you talking about like this very left-hand side
Yeah.
at low frequency? Yeah, I think that's just fluctuations, because when you take like basically the way you get this is you take a time stream, like you just read out your detector for 200 seconds or something, and then you Fourier transform it. So your low frequency components, you just have like less samples to work with, because you can only get like 2 sine waves in there or something at the very lowest frequency.
Okay.
So there's naturally going to be kind of more fluctuation at the lower end.
Okay, cool.
And yeah, the final upshot of all this is that I guess the best result we have at Caltech to date is 78% of kids below this noise threshold, which we're getting there. It's close. Yeah, and I guess 10 hertz is kind of so you have like, you know, it's a full frequency spectrum. You know, you have a noise equivalent power at each frequency, but we typically look at 10 hertz because that's the frequency we were chopping at, and that's like what's going to really limit the system. And yeah, and 10 hertz NEP of 0.1 attawatts per root hertz seems more achievable than ever, I guess. So thank you.
Thanks.
Thank you. Anybody have any questions? Maybe Kieran.
So why not jump faster?
I think it's just hard, like physically.
So you're like it's a little bit mechanical
Yeah, like
thing.
I haven't seen what sort of like chopper would be used for like a telescope, but
It's like, why not an LCD? You can do that at hundreds of hertz.
an LCD.
Yeah, right. Like a window that's transparent that you can electrically make opaque.
Oh, that's advanced.
You know, like the 3D glasses,
Yeah,
which have they switch each eye at like 120 hertz.
yeah. I think the additional complication comes from the fact that maybe I have there's a plot I wish I included, but it basically shows like the sky backgrounds. Let me go back a lot.
It's the LCD too awesome.
Yeah, like you would just have to find a way to make it really cold so it doesn't add noise.
Yeah, because the transparent state is certainly not like.
Yeah, like so you have this.
100%.
Mhm.
Or other thing.
Yeah. Like, because I don't know if there's LCDs that are qualified to be at like 4 Kelvin. Or if they design it for that.
It isn't likely.
Yeah. Maybe that's the future though. I don't know. But yeah, because there's basically a plot that shows this plot here with like the emission from different temperatures of a telescope, like different temperatures of your optics. And you have to be at like 4 Kelvin to get below this, which is what they're going to try and do, what we're going to try to do for Prima, for the far infrared stuff, that's another big bottleneck for like engineering difficulty, which I didn't even touch on.
Oh yeah, I guess I wanted to ask, how are they gonna keep a superconductor up on a telescope and keep it sensitive and working and everything?
Yeah, you basically just put a cryostat, like put the same sort of cryostat we have and just put it on a telescope, because put it on a space telescope. Yeah, because yeah, assuming you don't lose helium, you know that it's like a circular loop, and that if you can power it, it'll keep cold.
How would you power it?
This is again stuff I don't know very much about.
So then were you involved in the like building of the kids or more of the analysis of the noise?
My side is more like the testing analysis side.
So the ultimate goal is to put this on like a space-based telescope.
Mhm.
How difficult would that be, considering that it's a superconducting system?
Difficult.
Okay, yeah.
I mean, it's been done. Trying to think if they do like, there's been balloon missions done where they use kinetic inductance detectors and like other superconducting detectors. That's overall, I think, like easier, but still everyone I know who has been through that complains about it being like horribly stressful to make sure everything's gonna work.
Yeah.
But it's been done. Like there's been flight projects where they use kids. Yeah. I don't know if there's been anything in space. I don't think there has.
So
Yeah,
this
there
is
definitely has.
a relatively new way to
Yeah.
observe.
I think just putting anything that cold in space is also new. Like I know James Webb does some cooling stuff. It's mostly like passive cooling. And I know like the previous far infrared probes I mentioned, like Herschel, did also passive cooling to like 50 Kelvin or 70 Kelvin. So I think maybe like the extent of active cooling that is being proposed is like pretty novel.
What Kelvin does it need to be at?
The telescope optics need to be at 4 Kelvin.
Okay.
I think people are like maybe pushing that up a bit. They're just like, oh, we could take a somewhat of a hit, like 6 Kelvin without being so bad. But yeah, it's pretty cold.
Sick.
Better.
Yeah, that's a warm summer day, right?
It's positively balmy.
Yeah. I've also heard people talk about using kids for dark matter detection. Do you know anything about that? Or is it not?
I know of it. I know they have to care like way more about phonons in silicon.
Yeah.
Because they have to care a lot about like silicon dynamics and stuff. Because they're basically trying to detect like one nuclear recoil or one electron. I forget which it is. It's either a nucleon recoil or electron recoil from like dark matter scattering off something in silicon, and
I
then
think it's
the kid like collects the phonons.
Yeah.
So they have to also be really sensitive, basically.
These are silicon.
Yeah, our substrate is silicon.
Would it be better to use a different substrate? I guess because if you're one over active points on there, it doesn't matter.
Yeah, I think
some insulator, some oxide.
I don't think anything in the silicon, like the silicon wafer is basically what we print everything on, and then we put like our aluminum, like our niobium, our like dielectrics on that.
Yeah.
I don't think the silicon substrate itself like matters that much for the noise
This
performance.
is like semi.
Yeah, like the only reason I can think of it mattering is like if a cosmic ray comes through your wafer and like maybe other materials would like propagate phonons differently or propagate energy differently. But I think silicon is just like pretty standard.
Yeah, I talked to a guy who's working on diamond semiconductors, and one of the motivations was they're super, super robust against all sorts of super high energy.
Oh, yeah.
They get hot, and they like thousands of kelvins and still have a working transistor,
Oh, that's crazy.
and they can handle thousands of volts, so.
Yeah. Yeah, I guess we have to care about like energetic stuff only in the sense that like when you're in space, you have a lot more cosmic rays than like at ground because you don't have atmosphere shielding you. And so you actually have to do something just the wafer to make sure like a cosmic ray is not gonna glitch out like every pixel. Because it will do that if you don't like try and like space proof your device. Yeah.
So I think I understand the route thing, better, because you have your take, it's how often can you do a full band sweep of S2, right? So I
Yeah.
feel like you're sweeping across your gigahertz-ish range to look for the resonances. So the sine wave you're generating is in the gigahertz.
Mhm.
And you're computing its S21, but your readout speed is how often can you do that process, right?
Actually, this is something I didn't explain very well. Like you do that once, kind of once every so often to correct for drift and like figure out like has my resonator moved. But then what you do after that is you just take one sine wave for each resonator and like put it on this most responsive point that you found. And then you like from this formula, you can kind of back out like how much, say your tone moves this much in like S21, like say your transmitted tone changes that much, like how much has the frequency changed?
So you're generating that sum of sinusoids.
Yeah.
To simultaneously. Wait, so then how? Either you have a mix in there.
Mhm.
You have sums of sinusoids.
Yeah, there are like intermodulation products
Yeah.
that you
Because
have to care about eventually. I don't think
depending on how far apart your resonances are, your third order intermodulation would fuck with your phase measurement, right? I think.
yeah, I mean, I think it kind of just becomes like a noise floor, right? Because there's so many of them.
Right.
So as long as like,
The hard problem.
yeah, a lot of pixels makes things hard. But yeah, I think out of the things people are concerned about in like designing this, I haven't heard as much concern about like IM products as like other things.
I guess your tone powers.
Yeah, our tone power is like minus 110 dBm
Oh my God.
per kid.
Okay.
So it's like tiny.
Yeah, that was awesome.
Okay, if there are no more questions, I think we're gonna end there. Let's all thank Roger. And thank you.